Okay, let's take a look at the thermodynamics. So this is the borax solution. Borax was dissolved. You decanted it off, and that's going to be important for one of these. And then you did a titration. So let's talk about it. All right, so based on the Gibbs free energy value of room temperature and cold reaction, is the borax solution more spontaneous or less spontaneous at room temperature? More spontaneous or less spontaneous? So it's not asking whether it is spontaneous or whether it's not. It's the degree. Let's the data that I have for my students of a previous year, probably the delta G of room temperature after doing all the calculations is 16.2 kilojoules per mole. The delta G of the cold reaction was 16.8. So not much deviation, but the temperatures are actually not a huge difference. I think it was like 2 degrees to 20 degrees. In the grand scheme of things, that's not very much. So what we need to understand is where are we on this scale? So if this is the delta G scale, 0 is equilibrium. Um, a negative value would be spontaneous, and a positive value is going to be non-spontaneous. What that ultimately means is the closer we are to a negative value, the more spontaneous it is. So if we look at these two values, what we see is room temperature is lower. Okay, so if it's lower, that means it is technically more spontaneous because it's closer to the spontaneous value of negative. So lower, therefore, is more. I'm going to put that in quotes too. Quote, more spontaneous. I don't really need to. It is more spontaneous. But according to these values, they're actually non-spontaneous because, yeah, this is what we've got. So more spontaneous because the higher the temperature, the lower the delta G. So it's moving towards spontaneity ultimately. Yeah, so the higher the temperature, it would seem, equals a decrease in delta G. And so that is shifting towards a more spontaneous because it continues to decrease. So we would need to increase the temperature more to get more and more spontaneous. All right. The sample of cold temperature saturated solution likely warmed um, from the recorded temperature. Why is it important? Okay, so here we go. The sample, so if we think about how we did this, we have our little flask and we have our cold water. We did this before. And then, so that was step one. We cooled the water. Cold water. Step two was add the borax. Step three, this is an important part. And after you allow it to mix, so I guess ultimately step three is mix for 10 minutes or something like that. 10 mins. And then step four is you're going to decant the saturated solution. So you have removed all of the solid. So that's important. At this point, there is no more borax to dissolve. So when you get to the stage of, although once you have run your titration, the temperature has warmed up, ultimately you don't have any more borax to dissolve. So as long as you are decanting the saturated solution and you just have liquid, that means that there is no more borax to dissolve. So that warmer water could hold more borax, but it doesn't have access to it. So because you have decanted off that saturated solution, it doesn't have access to any more borax, and therefore the concentration of borax is locked in as soon as you decant it off. So decant the solution, this locks in the concentration of borax. I mean, potentially what could happen is if you cooled it down even more, you could have some solid crash out of that solution potentially, but that kind of locks in the borax as soon as it has dissolved. And warming to room temperature doesn't give it access to more. So that's the idea there. All right. Suppose some of the 100 milliliter equilibrium solutions were inadvertently included in the titrated sample. Sorry, some of the solid. Suppose some of the solid was included in the titrated sample. Okay. So if you figure what's going on, when you're doing your titration, you have a bunch of borax and you're adding HCl. If you have little bits of solid, this is undissolved borax. But as soon as the titration happens, so what's going to happen is the titration reacts with the borax, or borate, I should say, ion. What'll happen is because it's reacting with the borate ion, now there's less borate in solution, and so what ultimately would happen is the solid will dissolve because there is room for more borate. So the solid will dissolve, and therefore it will ultimately increase the volume of the titration. If you increase the volume of the titration, what we're doing is inadvertently creating a higher concentration. Well, we're showing that a higher concentration of borax is present. And if I have a higher concentration of borax, that means I'm plugging those higher values in, ultimately, which is going to increase my KSP, because KSP is equal to the concentration of the sodium ion times the concentration of the borax, or borate, I should say. So this is borate. So the concentration of the borate. Keep in mind that the sodium ion is actually determined by that borate concentration. So you look at that borate concentration and you recognize, oh, borate, the sodium is based on how much borate is present. So increasing increasing the volume of titration ultimately increases the borate, which increases the KSP value. That is the end result of having undissolved borate or borax present. All right, next one. Suppose the water was not cooled before adding the borate. Okay, so a couple of things. The water was not cooled. Okay. This borax, and the reason that we do it this way and we cool down the water first is it tends to saturate. What that ultimately means is the example I was used for my students is making sweet tea. So if you want to make sweet tea, if you add sugar to cold iced tea, it doesn't get very sweet, and the sugar just settles to the bottom. If you add sugar to a hot water solution of tea, that stuff is going to stay in solution. So ultimately, the supersaturated solution means that the water is going to hold more ion, in this case borate, than it should at the lower temperature. So what that means is if you add the borate at the high temperature, it's not going to crash out a solution. A normal solution, if it doesn't supersaturate, you would just end up with more solid on the bottom. But borax doesn't do that. What happens is it stays in solution and you have an unequal representation of how much borate should be in solution at that temperature. So ultimately, what you do is by creating the solution at a higher temperature and then cooling it, not enough borax is going to crash out. So ultimately, what you are going to end up with is an increase in borate in solution, which equals an increase in volume of your titration. And for the same reasons above, that equals an increase in the calculated borax, or borate, I should say, which equals a increase again in KSP. Same idea is you have more borate than you should have there, and ultimately end up in that result, result. All right, so next up, the literature values for enthalpy and entropy of the dissolved borax in water are 110 and 380. Again, units are going to be important here. 110 kilojoules, 380 joules per mole Kelvin. Determine the percent error. Okay, so percent error, we can do that. Percent error for your experimental determined values. So percent error, again, as always, your experimental value minus the accepted or the literature value divided by the literature value times 100. So for me, the students had an experimental value of delta H equal to 25.0 kilojoules per mole and a delta S of 30.0 kilojoules per mole. Oh, sorry, joules per mole K. So pretty far off. And so now we're just going to plug in chug. So 25.0 minus 110 divided by 110 times 100. I don't have to do units because they're all going to cancel out because they're all the same delta H. We end up with a 77.3% error. And my delta S, 30.0 minus 380, this is pretty massive, divided by 380 times 100. This is a 92.1% error. So pretty big difference, off by an order of magnitude almost, and off by a quarter in the other one. So yeah, that's the calculation there. All right. And make sure that you have them in joules and kilojoules. Make sure the units line up though. All right, so let's move on to the problems. Based on the KSP of the cold temperature determined in the lab, calculate the mass of the borax that would dissolve in 250 mils of water. So we kind of did this in the silver chromate lab. So first thing we're going to need is the KSP determined in the lab. The KSP that my students got for the cold reaction is 6.58 times 10 to the negative 4. And so what we need to do is we need to determine the molar solubility of that KSP, because I know that borax as a solid dissociates into sodium ions, 2 of them, plus the borate ion. So my KSP for this is concentration of sodium ions squared, concentration of the borate. There we go. And off we go. So 6.58 times 10 to the minus 4. And so now we are looking at the values. We don't have any borate present or anything like that. I'm going to end up with X amount of borate and 2X amount of sodium. So for every 1 borate, I should end up with twice as much sodium. And so these two are going to be based on each other. So I'm giving you KSP, which means I'm asking for equilibrium values. So the right side is going to be 4x cubed, and I'll rewrite this 5.8 times 10 to the negative 4. Divide both sides by 4, and you end up with 1.65 times 10 to the minus 4. Take the cube root, and you end up with 5.48 times 10 to the negative 2. I'm just going to call that 0.0548. And remember, X is every single borate represents 1 borax. So that is going to represent your molar solubility. So my X value is going to be important here. The 0.058, but 548 moles per liter is ultimately the unit that we're going to have there, molarity of the dissolved borate or borax. So we're going to use that number in a second. So I have 250.0 milliliters of this solution. We're going to end up in grams. So I'm going to convert this from 250 mils to 0.2500 liters times a fraction. I want liters to go away and I want moles to remain. This is the concentration of the borax, or the molar solubility, I should say. So 0.0548 moles per 1 liter. Liters cancel. So this is moles of borax that dissolves times fraction. I want moles to go away. I want grams to remain. And the next thing is going to be the molar mass of the borax. And so the borax, I'm just going to do the subscript here. Borax is Na2, B4, O4, OH4, and more importantly, 10 water molecules. So 10 coordinated water molecules when I plug that in. That turns out to be a mass of 401.403 grams per 1 mole. Moles cancel. And we do the calculation and we end up with 5.50 grams of borax is going to dissolve. So it's really important that we have the proper formula. That should be what you have, the molar mass of the borax. It has a lot of water on it, so it weighs a lot. So, but 5.5 grams should dissolve in 250 mils of water. All right, moving on. 20 mils of the saturated borax solution. Okay. 20 mils of saturated borax at 25 degrees is titrated with 14.38 mils at 0.15 molar. So we are going to calculate HCl, the KSP of the borax. Okay, so in order to get KSP, again, we know it's going to be sodium ions squared times the borate. So the borate, this is again, when you're doing a titration, you always have to represent the titration. So my titration was the same one from the lab. The borate plus HCl yields products. I don't really care about the products, but I do know that it is a 2-to-1 ratio. So 2-to-1 for the borate. Okay, so we're going to start again. We start with volumes when we're doing a titration. So I'm going to start with 14.38 milliliters of my HCl because that was the volume times fraction. I want the milliliters of HCl to go away. And because we're in mils, we're also going to be in millimoles of HCl. 0.1500 millimoles of HCl over 1 milliliter. Mils cancels. Right now I have millimoles of HCl, but I am looking for borate concentration because I need the borate concentration to plug in here. Okay. So times a fraction, you zoom in. I want the millimoles of HCl to go away. I want the millimoles of borate to remain. For every 1 borate, I need 2 HCl's. The HCl cancels. I do the calculation. I find out I have 1.078 millimoles of borate that was titrated. Okay, good. All right, so we figured out how much borate was present. What's the size of the sample? Well, it turns out it was 20 mils. So if I have 1.078 millimoles of borate in 20 milliliters of that saturated solution, this turns out to be 0.05393 molar borate. So we have the concentration of borate. Fantastic. So now we can just plug this value in, 0.05393 molar. But remember, the concentration of the sodium is actually twice that, 0.05393 molar and squared. So ultimately, it's going to be 0.05393 cubed, and you end up with 1.6 times 10 to the negative 4 as your KSP for the borax solution in that state. Okay, so KSP for the borax is 1.6 times 10 to the negative 4. Again, because I'm determining the amount of borate, we recognize that borax dissociates into one borax and two sodium. So make sure you take into account because it's going to be important for the third question on this post lab. All right. Finally, Gibbs free at what is the Gibbs free energy at 25 degrees C? Okay, we can determine that. So the Gibbs free energy, delta G, is equal to minus RT natural log of my K value. Again, you can use any K value you want here. We're going to use our KSP. And so off we go. Gibbs free energy. So my R value that I'm going to use is actually 0.008314. This is, remember, R is equal to 8.314 joules per mole, mole K. But I want to make sure that I am using kilojoules because I do want my answers. And so this value is just simply me converting to kilojoules, dividing by 1,000 beforehand. So 8.314 kilojoules per mole Kelvin, okay, times the temperature. Is it 29 or 25 degrees, which is 298 Kelvin? So I'll plug that in, 298 Kelvin. That's my temperature. Natural log of my KSP, which is above 1.6 times 10 to the negative 4, 1.6 times 10 to the negative 4. And off we go. So this math is pretty straightforward. Kelvin is going to cancel. My unit should be kilojoules per mole, and you end up with 21.7 kilojoules per mole when you do the delta G calculation. And it should be positive as well. Okay, so there's the calculations done for that next step. All right, so now we have a new scenario. Okay, so this is not based on lab stuff. This is a new saturated solution of strontium hydroxide. Strontium hydroxide, Sr is 2 plus, so I need two hydroxides. Strontium hydroxide is created at 0 degrees Celsius, okay, when 10 mils of the saturated solution is, and we have this value, 0.1 molar, 6.54 mils of HCl. That's the titration. Calculate KSP. Okay, so in order to calculate KSP, I need to know what the actual thing for KSP is. So strontium hydroxide as a solid is in equilibrium with strontium 2 plus and two hydroxide ions. So there's that means that ultimately my equilibrium is going to be, let's see here. My KSP for this is going to be concentration of strontium ions, concentration of hydroxide ions squared. When I do a titration, so we dissolve this in solution, and I've got strontium ions and hydroxide ions. And the important thing here is when we're determining this, so when we create this solution, essentially what happens is I have two things. I have strontium ions, and I have twice that hydroxide ions. I am going to be, they're free. These are free hydroxides. This is what I'm going to be doing a titration with. So H plus and OH minus is going to yield water. So it is going to be, because it's with HCl, HCl is essentially just going to be my H plus here. For every one HCl, I'm getting one hydroxide. We're going to deal with that in a little bit when we're going to kind of come back here and determine, do kind of a pseudo ice table, or we have to think about this just a little bit. But we are going to, again, when we're doing a titration, we are trying to detect my H plus or HCl, just bringing one H is going to combine with one of the hydroxides from that strontium hydroxide when it is dissociated to make water. So the important part here is this is a 1-to-1 reaction. So for every one H plus, I should have one hydroxide, which means I have, let's see, 6 points. So what I really want to know is what is the concentration of hydroxide, and we're going to take it from there. Because if I know the concentration of hydroxide, I can actually just plug that in because I do have that value. Uh, I do have that value here. All right. So um, yeah, I do have, there we go. That's what I'm looking for. I do have hydroxide. So if I can determine hydroxide, I can plug it in. It's going to take just a little bit of thought for what that strontium is, but let's get there. All right. So my titration value, I had 6.54 milliliters of H plus, again, from the HCl, times fraction. I want milliliters to go away, and I want millimoles of this H plus to remain. For every 1 milliliter, I have 0.103 millimoles. This is the concentration of my HCl. All right. Milliliters of H plus cancels. I am left with millimoles of H plus according to the uh, stoichiometric ratio, which is the next part. Millimoles of H plus to millimoles of OH minus. Luckily, it's a 1-to-1 ratio. Millimoles of H plus cancels. I can do this calculation, and what I end up with is 0.674 millimoles, 0.674 millimoles of OH minus. So I can, how big was the sample? The sample was of the concentrated solution, that 0.674 millimoles of OH was in a 10 milliliter sample. So that number of moles was in 10 milliliters or 10.00. So ultimately, I end up with a concentration of 0.0674 molar OH minus. Great. So I have the concentration of my hydroxide already. So my concentration of hydroxide, so I can replace that with 0.0674 molar, and I'll be able to square that. What's the concentration of my strontium? So for every one strontium I lose, strontium hydroxide I lose, I gain one strontium 2 plus and two hydroxides. So if the concentration of my strontium is of my hydroxide is 0.0674, that means my strontium ion has to have a conversation that is equal to 0.0674 divided by 2. It's half of that because I have twice as much hydroxide. Half of that turns out to be 0.0377. 337. So just half of that. So 0.0337 molar. And now we can do the calculation. So KSP is equal to, again, we have to make sure that we determine what those values are. 1.53 times 10 to the negative 3. And then it's probably important to recognize, because we've been dealing with a lot of temperatures here. This was at 0 degrees Celsius is what it said. Great. Okay. So with that information, what is the KSP of strontium? So I have information. The KSP of strontium hydroxide at 25 degrees is 3.2. Calculate the enthalpy of the KSP reaction. So enthalpy is delta H. Okay, we could do delta H. And so let's collect the data that we have. So based on this up here, my KSP1, I will call that the one from the previous problem, 1.53 times 10 to the negative 3. I will need the temperature as well. We'll call that temperature 1 of not 0 degrees Celsius, but 273 Kelvin, 273 Kelvin. Okay. My KSP2 is the information that I have here for the second one, which is 3.2 times 10 to the negative 4. And my temperature 2 turns out to be 200, and again, that's 298 Kelvin. Okay, so we have all of the information that we need, and now we need an equation, or we need the problem. We need to solve the problem. So natural log of K over K, KSP1 over KSP2 is equal to delta H over R times 1 over T2. We always put the second temperature first, minus 1 over T1. It doesn't really matter the order. You should always end up in the same values. And now we're going to plug things in. So KSP1, I'm going to plug in 1.53 1.53 times 10 to the negative 3. KSP2 is 3.2 times 10 to the minus 4. My R value, again, I'm going to want this in kilojoules, so I'm going to use the value of 0.008314 kilojoules per mole Kelvin. And I'm going to plug in a temperature 2 of 298 Kelvin, temperature 1 of 273 Kelvin. Now I can do math. Okay, so now that I have all this, the natural log of the K's comes out to be negative 0.739 delta H all over my R of 0.008314 kilojoules per mole times Kelvin. And now for 1 over T temperatures, I end up with a value of negative 3.07 times 10 to the negative 4, 1 over Kelvin, because that's what it should be. That is going to allow the Kelvins to cancel. And now I'm going to slide over, I'm going to divide both sides, or I'm going to divide by the value of negative 3.07 times 10 to the negative 4. We end up with 2.40 times 10 to the third is equal to delta H all over 0.008314 kilojoules per mole. Of course, the Kelvin is gone. My delta H comes out to be 20.0 kilojoules per mole. There we go. And that should do it. Yeah, so that's the solution for this. And that's the work. Okay, you'll find this linked in the video description so you have access to my notes. Other than that, yeah, I think that's pretty much it.